Hello, my name is Gladys Sucre and I want to welcome you to this flow assurance course. We are going to start with a brief introduction about the discipline, and we're going to talk about why did it originate and which topics does it cover. And then we're going to follow this by an explanation on each topic, starting with a brief theoretical introduction, followed by the steps that have to be taken during design and operations to understand which risks are present, the severity of the risks, and which measurements have to be taken to either eliminate, minimize, or remediate these risks. Please feel free to use the chat or send me a message if you have any questions during the course. So we are going to start with what is flow assurance? Why is this discipline exists really? Because the discipline is relatively new. And it's not because the topics were new, but because the importance of these topics started increasing when the fields moved farther and farther offshore, and the depths, the sea depths and the depths of the reservoir started to increase as well. And the operators were faced with large liquid slugs, solid deposits in wells and pipelines were being found, and that corresponded with a decrease in the production flow rates, and hydrates were proving to be costly and dangerous to remediate. And I think that if anybody knows something about flow assurance, they have heard about hydrates, right? So once this problem started to gain importance because their severity increased, we had to understand how do we do to model them and to predict what can happen during production. And to do this, we need to understand two things. We need to understand the fluid composition. And this fluid composition depends on the source rock, so the material that was in the source rock. Was it mainly vegetable? Was it in a lake? All that forms the base of the composition of the hydrocarbons that end up then in the reservoir. Then we have the expulsion and migration process to the reservoir, and more importantly, the pressure and the temperature at which the reservoir is, and how long have the fluids been in the reservoir, so the fluid maturity. For how long have these fluids been cooking at this pressure and temperature. And then there come also into play changes in the reservoir. For instance, if the reservoir is biodegraded, then the paraffin content decreases in the fluids, and that causes the wax to be less of a problem, and that can also stabilize asphaltenes. So all these characteristics end up in the final fluid composition, determine the final fluid composition that is in the reservoir. So we need to understand that. We need to measure the fluid composition in the reservoir. And then we have the thermohydraulics. And the thermohydraulics, we have two parts. We have one part that, again, we cannot change, as we cannot change really the composition of the reservoir. I mean, we do during EOR, but at the end, that's what we're going to produce at early life, right? And we have the thermohydraulics. We have, for instance, the ambient temperature. If the field is offshore and we have to transport these fluids in the seabed, then we cannot change the temperature of the sea, right? And we also have the reservoir pressure and temperature. That's kind of fixed. And we have other things, like, for instance, where are we going to put the hub that we're going to use to process these fluids? Is it going to be a local hub? Are we going to send it in a tieback farther away to an existing facility, or are we going to just send it directly to shore? And this we can control, and this will determine the severity of the risk and where are they going to happen. The same thing as what pressure is the first stage separators are going to be set, right? How much insulation are we going to put around these pipelines? These things we have control over, and they have a direct impact on the severity of the risk and the type of risk we are going to encounter during production. So this is what happens, right? In this case, for illustration purposes, we have a reservoir that has a water leg, an oil and a gas cap. And these these fluids are in equilibrium with themselves and equilibrium with the source rock, with the rock in the reservoir. So what happens then? We have a water that, since it's equilibrium with the rock, ends up with a lot of ions, right? It has potassium, it has calcium, it could have magnesium depending on the type of rock. And it has these salt acids that are coming from the hydrocarbon as well. And then we have the oils, where the larger hydrocarbon molecules end up, right? We have the saturates there, the aromatics, resins, and asphaltenes. And we have the smaller molecules on the gas cap. And these fluids have been there at the same pressure and temperature for centuries, and they are in equilibrium with each other. So nothing is happening anymore, right? But then we come and we put wells and pipelines, and we start producing to a fixed lower pressure, of course, in the facilities. And as these fluids depressurize, while they travel to the facilities, they depressurize, they cool down, and we break the thermodynamic equilibrium. And this can cause species that were in these fluids to destabilize and cause problems during production. So what type of problems can we encounter? What are these problems? Then we have hydrates, which are solids that form because small hydrocarbon molecules like methane, ethane, propane, well, and CO2 can also do that. They form crystals with the water molecules. And this can happen really quickly. And these solids then can plug wells and pipelines. We have asphaltenes in the other side, which are the largest molecules that are present in crude oil. And as the fluid depressurizes, these molecules can also become unstable and stick to wells and pipelines, and can crucially cause problems in the near wellbore area. We have wax, and this comes from the long-chain paraffins that can also precipitate as the fluid cools down and cause problems due to precipitation or gelling during shutdown. And we have scales and salts, and this comes from the water. Once these ions that were in the water we change the pressure and temperature, they can become oversaturated and can precipitate in wells and pipelines as well. We can also have emulsions, because now we are forcing the water and the oil to flow together, and this can increase the viscosity of the fluid and therefore increase pressure drops and cause production losses, and can also cause problems in the separators once the fluids arrive to the facility. And also we can have erosion and corrosion, and this is not typically something that flow assurance engineers do, but it is something that needs constant communication with the materials engineers, because we need to share data and what type of chemicals are going to be on the production to understand the erosion and corrosion risks. This figure can show us where normally these problems occur, because wax deposition could happen in the well, but it's not usual. It has to be a very paraffinic oil for that to happen. So normally asphaltenes and scales can cause problems in the near wellbore area and the wells, and we already, because of that, we understand they are very critical, let's say, because they affect a place that is not easy to access. And then we have wax, scales, and hydrates happening on the tiebacks. And we get to the first place when normally we have three-phase separation, and now we have the gas, the water, and the oil flowing or being transported in different ways to the shore. And in this single-phase line, we could still have hydrates in the gas if we're using a gas pipeline, if the gas was not properly dehydrated, and we can have wax deposition or wax gelling on the single-phase lines. So now we know why the discipline originated, what type of issues does it cover, but how do we evaluate this? How do we even start understanding which are the risks that are going to be present and how bad are they going to be? And first of all, we need a PVT analysis, and this underpins everything else, right? Because this is what is going to give us an understanding of what is the composition of the fluid and how the proportion of gas, oils, and solids are going to change in the pressure and temperature envelope in which our field is going to be operating or is operating. And we have then to evaluate the solid risk, and this has to also be done in the laboratory. And it's important to understand that the first screening tools, and we're going to be talking about that for each topic separately, but these first screening tools are normally cheap, they are fast, and they should be done, because they allow us to focus really quickly. Because we can know, is wax going to be a problem, yes or no? Can it be a problem? Do we have to keep considering the design, or asphaltenes? And that really allows to discard some things from the beginning. And then once we have the PVT analysis and we have analyzed the solids, we can put all that in a thermodynamic program that is going to generate a model that is going to give us that answer. In the pressure and temperature envelope, where are we going to have liquid, gas and solid together, and what proportions they're going to be at. And the second side of it is the thermohydraulics, because we have to input in a model, in a simulation model, then this thermodynamic envelope, and also how far are the pipelines, how deep are the wells, what is the insulation that we are evaluating or that it already exists. And all that is going to tell us the answers that we want. So it's going to tell us how big is the slug size, how long are we going to be producing only liquids and in which volumes, what are the minimum and maximum temperature and pressure that we're going to encounter during production, because that's going to determine the materials that we can use. And we have to do this during steady state and transients. We have to consider the borders of our operational envelope as well to be able to do this correctly and efficiently. And we can also investigate special operations or situations like well unloading, for instance. These softwares are now very potent, and they can start telling us when is water going to start accumulating, and it's going to let us evaluate, for instance, the options to avoid them. So use of current knowledge and experience. As we were talking about, this discipline is relatively new. And when these problems started occurring, we needed to put large margins in the design because we didn't understand the problems good enough, and we needed to be sure that they were not going to cause unsafe operations. But in the last decade, a wealth of research and production experience has been made available, and during current design and operations, we have to make sure that we incorporate this new knowledge that we have, so we don't end up over-designing facilities or overdosing with chemical injection. And another thing of this is that we need to evaluate what is the trade-off between cost and accepting production constraints while keeping our system safe. So, you know, if we want to produce under any circumstances, if we want to be able to start up every well first, for instance, that implies a cost, and we have to really understand if that cost is really going to be worth it, if it's going to give us enough return. So thank you. There is going to be a small quiz now that you can fill out just to understand and to also retain the knowledge so far. And then we're going to continue with the introduction, and we're going to talk about flow assurance during the project design cycle.